Okay, we are good to go. In the last class lecture, we have seen multiplication algorithm, and in today's lecture, we are actually going to see optimized multiplication algorithm. So, in this chapter, out of the arithmetic operation, we have seen that not only integer addition and subtraction is performed with only addition by our computer, but also this multiplication and division will be performed with only addition. And in the last class lecture, we have tried to theoretically understand how multiplication works and how we can find the values of these multiplications with only the addition and how we can actually generate the perfect result. We have seen an algorithm which can do this with only one addition, which is mn plus p multiplicand with product, and the result is stored in product register. That is the only addition operation we have done in this algorithm, and rest of these are actually shift left right. Okay, so this was the algorithm, and this is the hardware diagram. I need to remind you about this. This is the big picture of that hardware diagram. Multiplicand, multiplier, product are the three registers in here along with a 64-bit ALU. We have to take a look at the number of bits that is given to every register. Every ALU and these two register multiplicand and product are of 64 bits, and this multiplier are of only 32 bits. So whatever the bits we give in multiplier, we have to double that in multiplicand and product, and we have seen that in the simulation as well. Okay, now we are going to see this optimized multiplier algorithm or optimized multiplication algorithm. So this is better version of this algorithm and how this can be better. Okay, so if we want to better any algorithm, we can improve that algorithm in two cases. Either we are going to improve its time complexity, or we are going to improve its space complexity, right? Those who have completed data structure algorithm must know about these two things. Please respond. You know about these two things, that we can improve algorithm using these two things, space or time complexity. Remember about these two things?
Yes, sir.
Okay. So in here, they have improved the space complexity. They have improved the space complexity. So in here, the hardware diagram looks up all the memories it requires. So it has three registers: multiplicand, multiplier, product, and ALU. And these three are of 64 bits and multiplier are of 32 bits. Now, how can we optimize the space in here? We have to reduce the memory required to perform the multiplication algorithm in here. To do that, we may have to remove some register or reduce the number of bits, or both. I may repeat again. To reduce the space complexity, okay, so we have to reduce the memory needs to perform this algorithm. To perform this algorithm, we need this memory. Now, in optimized multiplication algorithm, we have to reduce the memory space required to perform the algorithm. To do that, either we have to remove one of the registers in from in here, reduce the number of register, or reduce the number of bits in here that these registers are taking, or do both, remove register and reduce number of bits as well. In this optimized multiplication algorithm, they have done both. They have removed one of the register and reduced the number of bits as well. Let me show you. Uh, okay, so this is the hardware diagram for optimized multiplication algorithm. In here, you can see multiplicand register, ALU, and product. There is no place for multiplier register in here like the previous algorithm. So this register is missing. So they have removed one register, and you can look at the sizes in here. Multiplicand were of 64 bits, ALU were of 64 bits, and product were of 64 bits. In here, only the product is of 64 bits, but these two are of only 32 bits. So they have removed one register, that is multiplier, and they have reduced the number of bits as well. So you can see how they have managed to reduce the space complexity. Please respond.
Yes, sir.
Okay, thank you for the response. Now, as we can see, there is no multiplier register in it. We already know to multiply two numbers, we need a multiplicand and a multiplier. Without the multiplier number stored in a register, we cannot perform the multiplication algorithm, right? Please respond.
Yes, sir.
So, to do that, they have stored the multiplier value on the right half of product register. So, actually, the product register now is divided in two parts, left half and right half. In the left half, it will have the value of the product. Initially, it is 0, like given in here that the value of the product is initially 0, normally in this multiplication algorithm. So, the value of the product will be on the left half of the product register, which will be 0. And on the right half of this product register, it will have the value of multiplier. So is it clear how we are actually reducing one storage, one register from here, multiplier register, but keeping that value on product register? Okay, is it clear how we are actually storing the multiplier on the right half of the product?
Yes, sir.
Okay, so now we have all values stored. Like initially the product 0, we have the ALU to perform the additions, we have multiplicand stored in a register as well as multiplier on right half of a register, that is product register. Now, normally when we have used this algorithm, we always checked the 0 number bit of multiplier, right? Please respond.
Yes, sir.
In here, multiplier is in the right half of this product register. So to check the 0 number bit of the multiplier, we have to check the 0 number bit of the product register, right?
Yes, sir.
This is what we have checked, 0 number bit of the product register each time. And we have found that there is two operation done. If the 0 number bit is 0, we are actually doing this. If the 0 number bit is 1, then we are doing a addition operation, then coming back to shift. And what is that addition operation? In here we need to add mn with p and store in p. Remember, mn plus p onto p. Please
Yes,
respond.
sir. Yes.
In this algorithm they are doing the same, adding multiplicand to the left half of the product, because product is actually not the entire product register. Product is placed on only the left half of the product register. So to add mn with p, we need to add mn with left half of the product register and store the result on the left half of the product register, right? Please respond.
Yes, sir.
Okay, so they are actually adding multiplicand to the left half of the product register and placing the result in the left half of the product register. As we have multiplier on the right half, we are not going to touch that. Okay, then what we used to do at last, we need to shift the multiplier register right one bit, right? We
Yes,
have
sir.
to shift the multiplier register right one bit. And in here, if we want to shift the multiplier right one bit, we have to shift product register right one bit, right?
Yes, sir.
So we are going to shift the product register right one bit. So we have multiplier on the right half of the product. We have the result of the product initially 0 on the left half. To add multiplicand with product, we are going to add multiplicand with left half of the product. So this is the addition we are going to do. Add multiplicand with left half, product left half, LH. Add multiplicand with left half of the product to store in the left half of the product. Okay, so we are going to see a simulation. As we already know the theoretical explanation of this multiplication algorithm. I'm not going to explain it anymore. So this is the simulation we are going to perform on this algorithm. Okay, on this algorithm. uh, optimized multiplication algorithm. Okay, this is the simulation we are going to see. So now I'm going to be in here. So this is 9 going to be multiplied by 7. So can you please tell me which one is multiplier and which one is multiplier out of these two?
So 1001 is multiplicand, or 0111 is
Uh, I can
multiplier.
hear you very low. Can you wait, speak a bit louder, holding your mic maybe closer to your mouth? Maybe.
Yes,
Okay.
sir. Yes, sir.
Okay. Thank you.
Yes. Sir,
So
1001 is multiplicand and 0111 is multiplier.
very good. So you are saying this is mn multi, this is mr, this is multiplier, and what will be the product initially? We have to find out. Let me erase all these lines in here. Okay. So we are going to delete every line in here to see the simulation perfectly. Okay, we are done and dusted. So this is the multiplication we have to do. This is multiplicand, this is multiplier. Okay, now we have the product register in here. Remember, in previous algorithms, we had to take multiplicand and product as the double of multiplier. But now you can see multiplicand will be half of the product and multiplier also. In here, 64 bits. Left 32 bit for product, right 32 but 2 bit for multiplier. So multiplier and multiplication will be of same bits. Product initially will be of double bits. Okay. So multiplication multiplier is of actually same bits, 4 bits. Product will be of 8 bits. In the left half, it will be initially 0, the original product in here. In the right half, it will be multiplier. Is it clear? Please respond.
Yes, sir.
Now, what we are going to do, this is the initial steps. Now we are back in this algorithm. We have to test the zero number bit of the product. If that is 1, we have to add a multiplicand to the left half of the product and place the result in the left half of the product. Then we have to shift the product register right on 1 bit, and we are going to repeat this process not for 32nd time but for 4th time, as we have only 4 bits in the multiplier. So what is the zero number bit of the multiplier? 1 or 0? Sorry, actually the product register. 1 or 0?
One, sir.
If that is 1, we are going to need to perform this addition in here. Left half of the product will be added with multiplicand to be stored on the left half of the product. The product left half is this 0. Multiplicand is always 9 in this example. It will not change. The addition is 9. 0 plus 9 is equal to 9. There is no carry. Why we have to worry about the carries? Now, as we have to perform these additions in here, we may get some carries in here. For example, if we add two 4-bit numbers and if there is 5-bit in the answer, then carry is 1. Otherwise, the carry is 0. As we are adding two 4-bit numbers, result is in 4 bits, so there is no carry. Carry is 0. Why we have to worry about the carry? I'm going to explain later. So now this is the left half of the product register should look like, and right half should be the multiplier. Previous step multiplier. So now what we have to do, as we have performed the addition and stored the result on the left half of the product register, now we need to shift the product register right 1 bit. Okay, we have to shift the product register right 1 bit. So how can we do this? We are going to copy this in here, merge these two, become make it 8 bits. How we can shift left? We have to remove the right sided bit, add a 0 at the left. Now we are not going to add a 0 at the left. We are going to add the carry at the left. So is it clear?
এটা আগে চলে আসবে, right?
Carry will be in here, yes. Now next line, next step, as we have completed this step in here. As you can see, this step completed in here, we have to go to top again. We have to check the zero number bit of the product again to check the zero number bit of the multiplier. Okay, so this is the zero number bit of the product. Now can you please tell me what it is?
1, sir.
1. If that is 1, we have to add left half of the product with mn to be stored on left half of the product. So left half is this 0100. Mn is always 9 in this example. As you can see in here, ms is fixed. We are not going to shift left, and this will always be same in this algorithm. So in here, this is mn, this is left half, this is the addition. 4 plus 9 is equal to 13, so there is no carry. Carry is 0. So this will be stored on the left half of the product, and right half will be like the last step for the multiplier. Now what we are going to do? Using the algorithm, we are going to shift the product register right 1 bit. So I'm going to copy all these in here. I'm going to merge these to make it 8-bit. Right-sided bit will be gone. This carry will be on the left. Now what we are going to do is we are going to make it 8-bit again. Now second step is completed. We are going to be back in here to check the product 0 again. Okay, so let me show you. Can you please tell me what is the 0 number bit of the product now?
1, sir.
1 again, so we have to add again. So this is left half of the product. This is multiplicand, always 9. As you can see, multiplicand is 9, so this is 9 in here. So if we add 6 plus 9, it is 15 in binary, so there is still no carry. So this will be in here in this product, and the right side multiplier will be the previous step multiplier. Now what we are going to do, we are going to shift this right 1 bit using the algorithm. To do that, I'm going to merge this number as 8 bits, delete the right sided value, insert the carry in here. Make it 8-bit again. So is it clear? Please respond.
Yes.
Now we are going to be back in for the fourth last step. And in this step, we are going to check the 0 number bit of the multiplier product register. And what it is?
So 1.
It is not 1, it is
Oh,
0.
sorry, sir. 0, 0, sir.
If this is 0, then we are only going to shift right. As there is no addition in here, there will be no carries available as well. So we are only going to shift these in here. Right 1 bit. To do that, we are going to delete the right-sided value. Right-sided value, add a 0 at the front. Okay, so this is it. This is the final product result. Okay, so is there any question? Please respond. If there is any confusion or queries.
So it seems easier because no left shifts are needed like the previous one.
It has less steps, so they have tried to reduce the space complexity. Doing that, they have reduced the time complexity as well. So it has less steps to cover actually. So I have given the simulation in here. Try to look at the simulation and do let me know in 5 minutes if you have any question over this or not. Do let me know. Otherwise, I'm just going to give you a task based on this algorithm. We are going to perform the optimized multiplier, and in that simulation, you are going to see there will be many carries. Okay, so you have to worry about the carries as well. I'm waiting for a response. Let me know if there is any query. I'm going to stop the screen share only to that presentation, right, where you can see the algorithm actually. Go through these steps again to check if there is any confusion in your mind. If there is no, I'm going to wait for 5 minutes. Then I'm going to give you a task.
Sir, which is 32 repetition it takes, sir, I want to do that.
30-second repetition means if the multiplier is of 32 bits, then we are going to repeat this process for 32 times to get the result. If multiplier is only of 4 bits, then we are going to actually cover 4 steps, or in 4 steps we are going to find the proper result.
Okay, sir.
স্যার যোগ করার পর কি আমরা রাইট শিফট করছি?
Yes, every time after the addition, if there is actually any addition, after the addition we have to shift the product register right 1 bit every time. Okay, I guess there is no question from you guys. I'm going to drop a uh, new problem in here for you guys. You need to find the solution of that. Okay, let me give it to you. I have given the problem in the chat box. We have to multiply actually 13 by 7. In here, you are going to get the carries in here that you have to worry about when you are going to shift right. Remember, when you are going to shift right, inside the carry bit on the left. So I have given the task in the chat box, 13 by 7. So do that and let me know your answers in the chat box. This is the only task you are going to do for today. Take 20 to 30 minutes to do that in case you need. After that, we are going to take the attendance to finish today's class. Okay. And we are going to see division in the next class. answer sir, there is some problem in your solution. Okay, try to find out. I think in the step two there is some problem.
Okay,
So
sir.
try to find out what is that. Okay, try to start from the start. Okay. In case you do mistake, and this is suggestion to all of you. In case you do mistake and find out that your result is not correct, if you try to find out in which step you made the mistakes, you are going to waste more time than when if you try to do it from the start and beginning from the beginning. Okay, so if you start from the beginning, it will take less time. If you use calculator and do write the answers perfectly from the calculator, whatever you get.
Yes, sir. I didn't take the value correct way.
Yes, yes, that is why your answers are not correct. Afanor Hassan, please do mention all the steps that you are actually performing while finding the answer. Your answer is correct, but I want to see everything in here with the solution. Okay, so how you are actually getting the addition result, what is the carry and all. Okay, Maliha Mehjabin, your answer is correct. Let me check all the answers. Okay, your answers are correct. Okay, everyone, please drop your entire answer in here so that I can check. Siam Hussain sir and Abdullah Fahd, your answers are correct. Others, please drop your answer. After 12 minutes, I'm going to take the attendance. By that, you can let me know in case you are facing any problem while trying to find the solution. Okay. So do let me know in the if there is any problem. I'm waiting for 12 more minutes. Then I'll take the attendance. Okay, for years one, Disha, your answer is right. Your steps are correct. Rest of them keep trying. If there is any confusion, do let me know. In 5 minutes, we are going to take the attendance. Okay, I guess no one is going to drop the solution. Maybe they are finding it difficult to find the solution. In case you have any problem with the basic theory, the idea of the optimized algorithm, please do let me know. Otherwise, I'm just going to take the attendance and that will be all for today's class. So, I'm going to take the attendance now. Tasnim Tobi Roishi.
স্যার আছি।
Okay, Aisha Mehjabin. Aisha Mehjabin is absent. Faria Jamun Disha.
Yes, sir.
Ahmed Ammar. Ahmed Ammar is absent. Aisha Siddiqa. Absent. Abdullah Fahad is present. Omar Shyam. Omar Shyam absent. Nigar Sultana Ritu.
Present, sir.
Zulkarnain.
Present, sir.
Afan present. Saleh present. Rakibul Islam Shotib.
Present, sir.
Adilita Mustafa.
Present, sir.
Ahmed Musa.
Yes, sir.
Hassan Shaun. Hassan Shaun absent. Mohibal Hassan.
Yes, sir.
Sir, Hassan Shawnati, sir, yes.
Present, sir.
Attendance given. Nusrat Jahan Sharna.
Yes, sir.
Abdul Al Mamun.
Present, sir.
Istiaq.
Present, sir.
Millat Hussain.
Present, sir.
Maliha Mehjabin is present. Farjana.
Yes, sir.
Rishad.
Yes, sir.
Samia.
Yes, sir.
Zahidul Islam.
Yes, sir.
Aparan. Shah. Quran Rifat is absent. Tariqul Islam Shahan.
Sir, Rifat Chila, sir.
Okay,
What is
Rifat
Samosha
attendance given. Tahlil Ajim. Tahlil Ajim is
Present,
absent.
sir.
Yamin. Okay, present. Yamin is present. Maria present.
Yes, sir.
Gaddafi.
Sir, Tahil Azim present, sir.
Yes. Gaddafi.
Yes, sir.
Rashidul Islam. Rashidul Islam Ujjol is absent. Atik Shahriar is
Present, sir.
present. Okay. Shakil Ahmed.
Present, sir.
Muhammad Tanveer. Muhammad Tanveer.
Present, sir. Sir, Tanvir,
Okay. Sumaya Yasmin.
Yes, sir.
Tariquzzaman Tuhin.
Present, sir.
Sir, twin ছিল।
Okay. Ariful Islam.
Yes, sir.
Sanjana Yasmin.
Present, sir.
Arhan.
Yes, sir.
Kia Motion is present. SM Naim.
Yes, sir.
Okay, I'm going to take the name of the absentees. Please respond if you are in. Aisha Mehjabin is absent. Ahmed Ammar absent. Aisha
স্যার
Siddiqa
আহমেদ
Shama.
আম্মার ভাই যে
Attendance.
কোভিড এর জন্য গেছে স্যার ছিল
Vaccine. He went for the vaccine.
জি স্যার
Okay, attendance given. Aisha Siddiqa Shama is absent.
Sir, present, sir.
Present. Okay. Omar Shyam is absent. Then
স্যার অমর সিয়াম আছে স্যার
Omar Shyam also present. Okay. So Tariqul Islam Shohan absent. Rashidul Islam Ujjol absent. Okay, these are the few students absent. Okay, so I'm going to set the attendance now. Is there any confusion queries? Any confusion or queries?